Hey guys, we're going to start section 12.6 today. As you remember, way back, I think in section 12.1 or 12.2, we talked about finding the missing parts of chords or diameters or segments that are inside of a circle like this. And we were able to use Pythagorean theorem because anytime a diameter and a chord intersect, we get that right angle there, which gives us two legs. And then, of course, the radius would be the hypotenuse. And we did that quite a few times in the very beginning of this chapter. Now the question comes up, how the heck do we find the lengths of chords that are not intersected by diameter or radius? And that's where these theorems come into play. Now, each theorem deals with very similar stuff to the last section. The last section was figuring out the measures of the angles. You know, the angles inside that are created by two chords or a secant and a chord or a secant and a tangent or two tangents. Now, we're dealing with how to find the lengths of the segments here. So theorem 12.6.1 says if two chords intersect in a circle, then the product of the measures of the segments of the chords are equal. Okay, now look, E is not a center. It would tell us if it was a center, and if it was a center, then we could use a different theorem. So I don't have any radii in here, and I don't have a diameter. These are not perpendicular. So according to this theorem, AE times BE equals CE times DE. You just multiply these and set it equal to the product of these. It's very simple. All right, here's two simple examples. Find the value of x, so 6 times x equals 4 times 3. Find the value of y, 8 times y equals 12 times 9. Sometimes they throw a y squared or an x squared in there, which makes it a little trickier, but still you guys can handle it. So those were figuring out the lengths of chords intersecting inside a circle. Now we go to segments intersecting outside of a circle. All right, similar idea, a little different though. It says if two secants are drawn to a circle from an exterior point. So remember, secants are, well, this would be a secant segment, but remember, secants are lines that intersect a circle in two different points. They're drawn to a circle from an exterior point, like this, point E. Then the product of the measures of one secant segment and its external secant segment is equal to the product of the measures of the other secant segment and its external secant segment. So this whole external secant segment is new, but pretty self-explanatory. If you look at this picture here, when you have a secant segment like this, AC is my secant segment, BC would be the exterior secant segment, okay? Or the external secant segment is what they say in your book. It's just the part of the secant that lies outside of the circle. That's it, so BC. So according to this theorem, AC, whoops, guess I should move my paper over, AE, ooh, I wrote that wrong. Look at that. It should be AE times BE. AE, the whole thing, times its exterior part, BE, is equal to this whole secant, CE, times its exterior part, DE. If you guys are looking at my notes, that was an error that was sent to you in my notes, okay? I just caught that now. So make sure you make that correction. If you printed off my notes, that would be a correction. It should be AE times BE, not AC times BC. That doesn't even make sense. Okay, so in other words, whole thing times the outside part is equal to the whole thing times the outside part. That's how I remember it. The next theorem says virtually the exact same thing, except the picture looks different, but pretty much it's the same thing. It says if a tangent segment and a secant segment are drawn to a circle from an exterior point. So we have tangent DC, remember it intersects a circle at one point. Secant AC intersects a circle at 2 points. They both come from C at point exterior to the circle, outside the circle. Then the square of the measure of the tangent segment is equal to the product of the measures of the secant segment and its external secant segment. It's a mouthful, but again, it's the same thing. Whole thing times the outside equals the tangent squared. You can think of it as AC times BC, the whole secant times its exterior part is equal to, think of it like this, the whole thing times its exterior part. It just so happens that both of them are on the outside. So DC times DC or DC squared. All right. So when you're doing examples like these or examples like the original one that we did, again, you just have to keep in mind where are these intersecting? Inside or outside the circle? If they're inside the circle, you just multiply each part of the chord times the other part and set them equal to each other. If they're outside, then you have to remember whole thing times the exterior part is equal to the whole thing times its exterior part. So in this one, it says find the length of RS. I'm going to call it X. I like calling it X. I think it's easier. We know PQ is 12, QR is 2, TS is 3. This is not drawn to scale, so don't judge me. It's not drawn perfectly. So since these both intersect out here at point R in the exterior, I'm going to write out the formula. We're going to say the whole secant, so PR times the exterior part, QR, is equal to the whole thing, TR,